In this video, we're going to talk about mapping for stoichiometry when we're incorporating percent yield. So percent yield is what you actually get when you run a chemical reaction over what you theoretically should get times 100%. So we're going to approach it from three different ways. In this first problem, we're going to try and determine the percent yield, and then in the next two problems, we're going to use the percent yield to figure out either how much reactant we're going to make or how much product we're going to get, assuming a certain percent yield. So in this problem, it asks you to determine the mass of copper that would be produced when you react 25 grams of aluminum and 32 grams of copper chloride. So I'm giving the amount of two starting materials, okay? And we're going to figure out how much product we can make from each of them. In a previous video, I went over an alternate way of determining the limiting reactant, but in this one, we're just going to figure out how much product we can make from each and go from there. So whenever we're given grams and we want to relate the amount of one material to another in a chemical equation, we first have to convert to moles. Take a trip down to Mole Town. So when we do that for aluminum, we divide by the molar mass, which is 27 grams per mole. We have 0.93 moles of aluminum. That would allow us, based on the chemical equation, you get 3 moles of copper for every 2 moles of aluminum. That means from 25 grams of aluminum, you would be able to make 1.34 moles of copper. So now we'll take a look and see how much we could make with the copper chloride. Given that we have 32 grams, and it has a molar mass of 134 grams per mole, we only have 0.24 moles of copper chloride. And since it reacts in a 3-to-3 ratio, or 1-to-1 ratio, with copper, you would only be able to make 0.24 moles of copper from your copper chloride. So that's going to be our limiting reactant, and this is going to be our theoretical yield in terms of moles. Now to figure out what that would be in grams, we simply multiply by the molar mass of copper, and we would get a value of 15.2 grams. Please ignore sig figs in these examples, okay? So that's what our theoretical yield should be. If we convert all of our reactant, our limiting reactant, to products, that's how much copper we could make. But if we ran the reaction and we were only able to get 12.4 grams, then we didn't get everything we were supposed to. And when we divide that 12.4 grams of actual yield by the 15.2 grams of theoretical yield and multiply it by 100, we see that we only get 81%. So in this reaction, we were determining the percent yield given the amount of reactants, theoretically determining how much product could be made, and comparing that to the amount of actual yield we have. In this problem, I'm going to do it in a different way in terms of how I'm doing the mapping. You can do it either way, it's completely fine. In this one, I'm showing how you can do it by just doing a string of dimensional analysis instead of putting all your calculations within your map. Either way is fine. So in this problem, it says, assuming a 58% yield for the reaction, how many grams of copper chloride would be required to make 28.6 grams of copper? So we would say, all right, we're trying to actually make this much, but we know our reaction isn't going to run at 100% efficiency. So we're really going to try to make more. So if I know that I actually need to make this much copper, and I know that it operates at a 58% yield, we can use our percent yield as a conversion factor. You only actually get 58 grams, that's a B there, for every 100 grams you try to make. So when you do that, that means you really got to try to make 49.3 grams of copper. And so that's what we're going to shoot for. 49.3 grams of copper is equal to, based on the molar mass, 0.78 moles. And since we use up 3 moles of copper chloride for every 3 moles of copper we make, that's a 1-to-1 ratio, or 3-to-3. That means we would need 0.78 moles of copper chloride. And using the molar mass, we would get that that would be 102 grams required. So in this problem, you were given a percent yield, and whenever you're using percent yield, it's really a relationship between what you actually get for a product out of what you should have gotten for a product. So only if you're going to use the percent yield as a conversion factor, only apply it to the product. Don't try and apply it to a reactant. Okay? In the next problem, we're going to use percent yield again. And in this case, it's one where we're given each reactant. We've got to figure out which one's the limiting reactant. And then we're given a percent yield to figure out how much we would actually get from this process. So we're given that we have 22.8 grams of aluminum, 54.8 grams of copper chloride. Again, whenever we're comparing different substances, we convert to moles, and I show that in this step right here. For each of these, and you can see that we have 0.84 moles of aluminum and 0.41 moles of copper chloride. So then from that, we figure out how much product we could make with each. Turns out copper chloride would be our limiting reactant again. You could only make 0.27 moles based on the balanced chemical equation, and therefore that's less than 0.84. We can move forward with this one. So using our copper chloride as our limiting reactant, we would then say, all right, we can make 0.27 moles since it has a 133 grams per mole. Theoretically, if we use up all of our limiting reactant, we should be able to make 35.6 grams. However, our reaction only runs at 70%, so that means you get 70 grams of actual yield for every 100 grams of theoretical yield, and that means we would only end up getting a 25.5% yield. So we looked at 3 different ways we can calculate percent yield or use percent yield in a stoichiometry problem.